So today I want to look at what happens when we take an autonomous differential equation that has some parameters in it and then do our phase plane analysis. As you vary parameters, you can modify the differential equation, and if it's an autonomous differential equation with a phase line diagram, then as you change the differential equation, you can watch the critical points move around on the phase line, and this can lead to a really interesting way to analyze systems. I'm going to base the entire discussion on one example, and it's going to be one of these epidemic models, but this is a slightly different one. So imagine you've got a population with n people, and some people can be infected with a disease, and they can infect others. Everyone who's not infected is susceptible, meaning they can be infected. So there are basically the population is made out of two kinds of people, the infected and the susceptible. If the population consists of n people, then we've got this relation that I plus s is n, where n is a constant. So we're assuming that no one dies, this doesn't kill anyone, but also no one fully recovers. Like, you can recover, but you would not become immune. So you can go from susceptible to infected, and then you can maybe you can recover and go back to susceptible, but you will always you will never enter a pool of immune people who will not get reinfected. So that's just the model that we are looking at. And actually, we're going to keep it very simple to start with. So you cannot even recover. So let's just say susceptible people can become infected. And that's it. That's the only mechanism we will introduce to begin with. Then we'll do our analysis. Then we'll introduce the possibility of people recovering. So what's the rate at which susceptible people would become infected? So if we decide what that rate should be, then that will tell us what is I prime in our differential equation. Well, the rate at which susceptible people would become infected should be proportional to the number of interactions you expect per unit time between an infected and a susceptible person. So this is a lot like the infection model we discussed earlier. In fact, it's basically the same one with things renamed, where it's, we had these like white dots for susceptible people and then some red dots for infected people. And what we want to count to see sort of what's the rate of increase of infection is per unit time, how many of these interactions do we expect between a red and a white, between an infected and a susceptible. So we would count these, but we wouldn't count like this one. We wouldn't want to count infected and infected interaction. So this will be the rate at which the number of infected people increases. So this is di dt. Let me write it like this. Is going to be proportional, let's say with a being the proportionality constant. So it'll be proportional to the number of interactions we expect between susceptible and infected people per unit time. That should be the product. Susceptible people times infected people. And these are functions of time. So why this product? Well, just think about the diagram with the white dots and the red dots. How many edges do you expect there to be that connect a white dot to a red dot? Well, s times I, except possibly a fraction of that in any given time, assuming everyone's like mixed up randomly all the time. So you would just take the number of white dots times the number of red dots. That's how many possible edges you can connect between a red dot and a white dot. Okay, so this is our model. And right now, it's actually not looking so good because there really should be just one unknown function in order for us to have a differential equation in one dimension, like the ones we've been studying. But right now it seems like there are two unknown functions, I and s. However, there is a relationship between I and s, which is that I plus s is n. So if you take this relationship and apply d dt, so take this equality and apply a time derivative to it, then what do you get? di dt plus ds dt equals 0. We're assuming this is a constant in time, that it does not change in time. So no one's dying. The population remains n people. So then this tells you that di dt equals negative ds dt, right? Oh, actually, that's not particularly helpful here. We might want to pay attention to that later, but right now, how about just solving for one in terms of the other? So I is n minus s, or s is n minus I. So how about we get rid of s here, and then write n minus I. And there's our differential equation. Let me write it in a nice, cleaner way. A n minus I, where I is the number of infected people. All right, well, this is an autonomous differential equation. So we can do a phase line type of analysis. So this looks like I prime equals, and then some function of I, right? Where the function of I is this. And it's a function of I alone. No explicit time dependence is showing up. There's only time dependence through the way in which I depends on time. All right, so let's draw our phase line, which is the I-axis, the number of infected people. And actually, I'm putting these arrows as though the phase line is this infinite line, but it has solid endpoints, right? The number of infected people cannot be lower than 0, and it cannot be bigger than n, which was the population. So remember, n was the total population. So it's more like a phase line segment rather than a phase line. And let's find the critical points. So let's see. To find critical points, I should solve the equation, this equation, right? So set the right-hand side equal to 0. Well, that happens at I equals 0 and I equals n. So right here and right here are the critical points. And that means these are equilibrium solutions. That should actually make sense. If the only mechanism that we've got is that susceptible people can become infected, and that's it. No one can recover, no one can die. Then, if no one is infected, you would expect no one to become infected. So 0 is stable. And if everyone is infected, then it would just stay that way forever. So if no one is infected, it stays that way forever. If everyone is infected, it stays that way forever. And you can probably guess the stability properties of these. I mean, probably if a few people are infected, it's just going to increase. So you'd expect something like that. If you were to plot a times n minus I against I, then what would that look like? Just for fun, or to justify the sizes of the arrows here. So here's I. Then I've got I equals 0 here, and I equals n here. Then if we were to plot the function, so remember our differential equation was I prime equals a n minus I. So if I were to plot I prime against I, what would that look like? Well, this is a quadratic, so it's a parabola, and if I multiply through here, I have a n I minus ai squared, and a is a positive number. We're assuming a is a positive number. So since the coefficient in front of the I squared is negative, I know that this is a parabola of this shape rather than this shape. And these are actually just the zeros of the parabola, right? That's where it equals 0. So it's something like that. So that's I prime against I. And what this plot is telling us is for each number of infected people that you could possibly have, for each state that you could possibly have, it's telling you, well, just look up at this plot and you can read the rate of increase of the number of infected people. It's increase since it's positive above the axis rather than below. So if there's just a few infected people, then the number of infected people increases kind of slowly, but it does increase. If there's a lot of infected people, then again, the number of infected people increases actually pretty slowly, but it does increase. So with a lot of infected people, the number of infected increases kind of slowly. And if you've got, like, I guess n over 2 infected people, then that gives you a situation where the number of infected people increases the fastest. So that kind of justifies the sizes of the arrows that I'm putting here in my phase line segment. Okay, so there was nothing very new here so far, and I'm just setting this up so that we can do something a little bit more complicated with it. And what I want to do is introduce a rate of recovery, and I'll do that in the next video. There you will see a parameter, a recovery rate, where when we vary that parameter, the critical points start moving around. And you can look at what different rates of recovery, what situations different rates of recovery can actually lead to.